This is a tutorial for making variable resolution MPAS meshes, and also like initial condition setups for MPAS using the compass environment. And Mark and Zyler are contributors to this.
Okay, great, thank you. So I'm going to flip to my second slide first, and let's see. First, I got to share. Here we go. Okay, and can everybody see my slides on the left and a terminal on the right?
Yes.
Okay. I'm gonna rely on Zyler and Milena to tell me if anything's going wrong in my presentation view. Okay, and so if you would like to follow along, that would be great. That's what I'm making this for. And so I put a little Unix variable here, username, and so then you can just copy all of these instructions directly. And I decided to do this just on Scratch, so we're all on the same location. If you do it later yourself, you're free to put it on whatever place on disk that you want. And I just did the exact same thing. So I just did this set of instructions here, and so I grabbed, I cloned the MPAS repository with the default name. Okay, and then there was a mix-up in the instructions for the order. Turns out the order is important here, and so this first one is for bash, although you can just run them all and it'll give you an error if it's the wrong shell. And then grab these second two, and you've loaded your modules. And then I went down a little past the page. You can do the make, and we're just going to let it chug away. The GNU is faster, it takes 3 minutes, but we're just going to have it make in the background while, oops, did I go to the wrong place? Sorry. Aha, I didn't copy everything. Okay, and so if you just copy these in order, and then there's just the two things here, whether you're on bash or C shell, one or the other. And then I'm going to do the make command, and then I'm going to go back and talk while this is chugging along in the background. And hopefully there's not too much trouble. Huh, it's kind of slow. It's probably slow because everybody's getting it at the same time. Okay, so we thought it would be nice to give everyone an introduction to the mesh generation process. And I think this is a really good time. Here, I'm going to put my make command in here right now. That's going to go on in the background. And I'm going to go to full screen here. Okay, and I'd like to acknowledge the contribution by a number of people that have made this a very nice system to use. And in particular, Doug Jacobson kind of kicked off the compass thing. It's what I always call his magic wand. And Darren Nguarda is responsible for the jigsaw development, which lets us do all this very quickly. And then a number of other people, Steve Bruce, Phil Wolfram, and Matt Hoffman, along with me and Zyler. Okay, does anyone have a question about slide 2, the compiling? Okay, so let me give you an overview.
Please remember to mute yourself when for asking a question.
Okay, so you present. Here is the steps that we're going to go over today, and it's really just these 4 that we're going to discuss today, and then there's some other functionality in Compass that I'll show you as well. So Compass is for configuration of MPAS setups. Setup's a little redundant, but it made such a nice acronym. And so this is a system that allows us to automate the generation of these meshes. And I always say that the variable resolution meshes, it has all of these advantages going into coastal regions and adding resolution, but you can configure your mesh 1,000,001 ways. And so it adds a lot of complexity. And so what we're trying to do with this compass system is be able to harness the power of this, but still be able to do it in an easy way. And we'll see. Hopefully I can convince you of that by the end of this. And so really, there's 4 steps in this part of the process. The first is that on a simple lat/lon grid, you define what your target resolution is in kilometers, and that's called cell width. And so that's what we call defining the base mesh. That's the first step, and we're actually going to do all this today. And then from there, Jigsaw as an input takes this simple cell width function and kind of does the hard work of the whole process, which is to create the Voronoi tessellation. And so that's what we see in the second image here. And then there's a number of things that have to happen for the ocean and sea ice meshes to remove the cells that are fully land. So that's culling the mesh. And then we have to initialize everything else that we use in the model: temperature, salinity, layers, bathymetry, and so forth. And so all of the images that I'm showing here in these samples are from the CUSP, which is the Coastal US Plus. This is a version that we have out for discussion right now. Compass it's within the MPAS repository, and these things are used for MPAS ocean, MPAS sea ice, the specific steps that I'm showing in the tutorial today. But MPAS land ice also uses the Compass shared functionality. Okay, so this is the slide oops, no, I'm gonna go back. All right. So one of the steps, the last one, initial state, uses the actual MPAS executable. So hopefully, I talked for 3 minutes at least. So your MPAS executable is probably here. If you do an LS, it's here as the ocean model, but then it also auto-generates sample name list and streams files in the same directory. So typically this is used for the forward model, but there's some initialization functionality in here as well that we'll talk about in a minute. So for anyone who's come in recently, there's a link on the chat, and let me know if you can't see it, or maybe we should post it again. And if you click on that link, then that allows you to copy and paste from these slides. So unless you can type really fast and precisely from what you see. Okay, and so the first slide with instructions, slide 2, was just to compile the code, that's all. And I'll just mention at the end here, I have a link, which is that the instructions I have for the tutorial today are specific to LANL, IC, and the GNU compiler. So it has those modules there. But I have a link right here on Confluence, and I know there may be some people that aren't on Confluence. And this, when it comes up here, we have instructions with the modules and everything for all of our standard machines and for your personal machine at home. And there's a larger variety of things that are explained on that page. And I also put a PDF version here in case you don't have access to Confluence. Okay, so I'm on slide 4 now, if you're following along. And this first little bit is just to give you a username variable in your Unix environment there. And so if you did it right, then when you do echo username, it just gives your moniker, and that's just so you can copy and paste stuff. Okay, so far all we've done is set up the repository, but all of this Compass stuff is inside the MPAS repository, and that was an intentional decision that we made so that so a big part of Compass is making sure that these name lists and streams files match the executable as you run it. And so since it's in the repository itself, we can make sure that that's always true, that those things work together, that your test cases work with your name list and streams files. Okay. And so here, these are a little bit redundant. If you are in your directory where you just compiled, then you can cd into the COMPAS directory, testing and setup, and then into COMPAS. Okay, and then in case you were doing this fresh, I just put the source again, but this was the same on 2 slides ago. Okay, so let's just stop for a second. And is everybody here? And if it turns out that you had trouble with compiling or something like that, you can still keep going with me. But hopefully people are in this directory. So in testing and setup COMPAS, and then you can see this list of files. And can I get some feedback? People seeing that?
I do.
Okay. This is what people complain about, talking into the void.
I know.
Okay.
Yes,
so hopefully you can.
Yes.
There is
Okay,
a chat.
Andrew said good for me.
Andrew, yeah.
Okay, good. So maybe another thing we can do, if you don't want to interrupt, if you're having some trouble, you can go on the chat, and Milena or Zyler can keep an eye on the chat as well, so I don't have to stop talking. Why don't we do that? Okay, so here there's a list of tools. If we look at all the Python scripts here, you can list the test cases, clean the test cases, manage a regression suite, and setup. So we're going to go through some of these things today. So the first thing is, if you just list the test cases, then there's a whole bunch of them there, and that includes the land ice test cases as well. And so you can see what these little different classifications are. If you do list test cases -- help, then there's different labels on these things. So the core is the ocean or the land ice, a configuration, a resolution, and then a type of test. And so there's all these different cases. And so if you're looking for a particular one, we're going to do a low resolution one in the tutorial today. So this quasi-uniform 240 kilometer resolution. It's low enough resolution that it only takes a couple minutes to run, and we can all do it together. And so here, these are all the test cases that are for the QU240. One of them is the init test case, which creates the initial condition. And then there's a whole bunch of other ones that we use for testing at this low resolution. So COMPAS is used for both initialization and for running the forward model and regression suites and everything else. And so here, if you want to look at all of the initialization cases, here's all of them. So there's a EC 6030, Southern Ocean, Arctic Refined Mesh, and so forth. So that's where they all are. Okay. And so then if we go to slide 5, and maybe what I'll do, see if I can do this, make it a little bit bigger. There we go. Okay, and so the main thing that you have to do to set up COMPAS is to use a config file. And so if we look at this general.config.ocean, okay, then it's basically a bunch of paths to fill in. And so if you're doing this on your own, or if you're doing it on a new machine, you have to download a few repos and link to the right paths and so forth. So there's some initial condition, locations, and so forth. I'm not going to go into the details of this right now. Instead, I'm going to give you the answer at least for Grizzly, for IC, you can just copy mine, okay? And so if you take this first one on slide 5 and copy here, and so I called it training, so it's different than the default ones there, okay? And so if you just look at this, then even though I had you compile your, here, I'm gonna scoot this over. So I had you compile your code a minute ago, but this is pointing to my directory. So if you want to, you can change that moniker to yours. It doesn't matter. You can also just use mine. And then if you look down here, there's a couple of other repositories. Those should all be accessible to you. So this is all just usable as is. But the main message is if you're using this on a different machine, then you have to download a few repositories and alter this. And then you can always ask me or Zyler later if you have trouble with that on a different machine. Or also this link on slide 2, this one at the bottom right here, it gives instructions that are more general. Okay, so I'm back on slide 5. All right, and so if we do this again, we're going to do the list test cases, and we're going to look for all the initialization ones. So we're going to do this low resolution one today, and that it just numbers all of them from beginning to end. This is number 74. And so the easy way to do this is we're going to do a setup test case, and we're just going to grab that number 74. And so here I'm going to do setup test case. If I do a -- help, it tells me what all my different options are, long and short flags. But here I gave you the long flags because it's a little bit more clear. Okay, but basically you're giving it your config file. You have to tell it whether to use MPI run or srun or whatever for your runtime. And then where are you going to put this configuration? Where are you going to do it? And we're using your username again, so it's going to be in your directory. Okay, there it is. And a backslash is just a continue in Unix. And so then it tells you what it set up. Okay, it set up all of these things. Okay, and so then you can go to your work directory, and it also tells you exactly what the paths are that it just created. Okay, and so if I go to slide 6 here, the next thing we're going to do is run it. Now, for the first couple of steps, you could just do that on a login node, but for running MPAS for the initial state, you have to have a compute node. Okay, and so we're going to do this, and everyone's going to do it all at once. So we'll see if it takes a little while. I got in, that's good. And so then when you log in, we're going to grab these again. Okay, and so you source and load your modules. Oh, I copied the C shell one in there, which gives me an error. Okay, and then we're going to go to the directory that we just set up. And oh, you know what? Sorry about that. You guys are probably doing the same thing as me. You have to grab this little username thing. The little username equals who am I? It's a cute little Unix command. You have to do that again. Should have done a set env. Okay, and so now I can cd into this with the username. Okay, so if I do pwd, I'm here. Okay, and if I type ls, these are the steps that I'm talking about. There's a base mesh, a cold mesh, and then I'll talk about that later, an initial state, and then you run the whole thing with run.py. And so I'm just going to do run, and then it goes through the whole thing. It's going through those steps. So why don't I open it up now and see if anyone got stuck or is having trouble.
So I posted in the chat, but if anybody had trouble getting an allocation, let us know, because I can log out. I obviously don't need to be following along. Free up a node.
Okay, so this is the point where if we were in the challenge room, I would walk around like a teacher, but I can't. So you all have to be self-sufficient now. Okay, so while that goes on, it only takes a minute here, but I'm going to go ahead and talk. And so here's slide 7. I'm going to go to full screen. No. Okay, and so a few slides ago, I had the overview. Okay, 1, 2, 3, 4, and those are exactly what we see on disk, what's running right now for the low resolution. And I'm going to go and talk about a little bit of detail with each of those. Okay, and so when the run command that we just ran, it runs all of these in sequence. But you can run each of them individually, and it provides more detail on the output. So we can look at that in a second. So you can CD into each of these directories, and the point of this here is to kind of isolate the files involved with each of these steps, and also so it's less to deal with on each step.
Mark?
Yes.
I have a question. So the run.py, the Python run that you ran before, so that one was, so what is the difference with the one that I see here?
Okay, that's a good question. So here it's done. So there's 2 levels in the directories. So here I am in the init, and inside the init are all of these different steps.
Okay.
And so then if I do an ls on all of these, there's a run.py in every single one. And then if you look at this run.py, oh, that was too much. It goes through and it runs the steps in order. And so if you don't know anything about how things are supposed to run, you can just cd into the directory, into the driver directory, and run that, and it does everything for you. But a lot of times it's nice to go into one of these directories and just look around a little bit and see what all is being made and what all it points to. And what we try to do is everything that you need, there's links to the files here. We try not to have it pointing to files that are hidden on a path somewhere. If you need files in here, the links are in here. And so then if you run in here, it's a bit more verbose with the output. So for this base mesh, it goes through, oh, it was a little bit quick. But see, it shows that it built this cell width array, and then it's running Jigsaw. And then it goes through all the Jigsaw steps, and then it says it made the base mesh.nc. And so you can see everything in here.
I see.
So it's really just whether you want to do the level up, you run it all, or you can go into a subdirectory and do it more granular. And for high resolution, if you ran out of time on your queue, say, or something went wrong, it's often nice to not rerun the full sequence, to just rerun what you need.
Sure.
Okay, so then for the first step, the important file is called define-basemesh.py. And for this QU240, the one that we're running, it's so simple, I just pasted it here, which is that you say that you're going to define your LAN grid by 10 degrees. It's a constant, so it doesn't matter what the resolution is in LAN space. And then you say, I want all of my cells to be 240 kilometers. And so if you went in here and you changed this to 60 or to 10 or whatever, it would do a global mesh with the goal of having all of the cells be that size. So it's really that simple. And then the complexity that we'll talk about later is, if you want layer upon layer of different resolution in different places, we have tools to do that. but fundamentally, you're just trying to create this variable cell width as a function of lat/lon. And then the end result of this is a netcdf file that's cell width as a function of lat/lon. And then this PNG file is auto-generated, which is exactly this. And so if you grabbed this one, it would just be a constant, which is 240 everywhere. Any questions on this step? Okay, and then step 2, which is in the same directory, is that it runs Jigsaw. And so it reads the lat/lon file right here that we just created. And then Jigsaw has a bunch of files that it writes along the way. Jigsaw is written in C, but there's a Python interface. There's also a MATLAB interface. And there's a lot of options that we can take advantage of in Jigsaw as well, which Darren has talked about in previous talks. So there's various options there. But in the end, Jigsaw produces a base mesh. Well, yeah, it produces these files, and then we create a base mesh.nc file. And that is the cell centers and the connectivity of the cells. And we also have a VTK file that you can view in ParaView. Okay, so that's the end of step 2. And I'll just let people interrupt me if they want, but keep going. Okay, so I'm on slide 9 now. And then the next step is to remove the land cells. And that turned out to be more complicated than we thought originally. And so if we go into the second step, here's the cold mesh. So we can CD into there. And just like all of these subdirectories, you can run this one individually, which you're welcome to do now as well. And then you get to see a little bit more of what it's doing. And for some reason, the cold mesh, the cell culling is a little bit slower than it used to be. It may be a library loading thing or something. But there's a number of things that we do in the cell culling step that turned out to be quite important as we started running simulations in E3SM. So here, let me see, view. And I tried to summarize these here. So fundamentally, for the ocean and the sea ice, we cull all of our land cells. And so that's for efficiency. There's no reason to run it on there. On a structured mesh, you have to keep your land cells, but then you try and get rid of the partitions that are all land. And so we have a coastline data set that's defined. And then there's a flood fill algorithm, and we remove the inland seas. So basically you try and figure out what's land and what's not. And then we mark the cells for culling. But then there's some other details involved, and one is on the next slide here, which is that if you think about a finite grid and a coastline, all we do is decide whether a grid cell is inside or outside of the coastline by the cell center. But that can produce some really funny things, especially at lower resolution, because really for ocean dynamics, it's important whether basins are connected or not. And it's less important what the exact shape of the coastline is. I mean, you can only do so much to adjust the coastline. And so here's an example with Japan, and it was connected with whatever you call this here, I forgot. And so it actually limited the flow around Japan. And so we have a process that's really quite easy now, where you can make a GeoJSON file and just define lines, and you can call it either a critical passage, which is these red ones around Japan, or a critical blockage, which is the yellow ones. And so then when you run this cell culling step, part of it is to force it, as you see on the right here, to get the blockages and the passages correct. So as you're doing this, and it changes sometimes with resolution or what you're interested in or whatever. We were just talking about shipping channels earlier today for the coastal project. And so as you do this, if you see things that you're unhappy with in your mesh, we can add these things quite easily. And so it's good at this step after the culling or at the end of this whole process, you really want to take a good look around a new mesh and make sure it's all suits your needs. We also have
so Mark,
yeah.
Just a quick point on that. I could be wrong, but I think the way things are currently set up, you either use all of our blockages and passages or none of them. So I don't think you get the option to pick and choose, but that would be something we could look into in the future.
Right. Yeah, I guess mostly if there's some blockage or passage that somebody sees is missing, we can usually add it, and it's fine to have it on all of the meshes. I mean, unless someone's getting into some really detailed things.
Right. I think that's our current assumption, is that everybody would use the same. Yeah.
Yeah. And so if we glance back here at what we just ran, it has quite a bit of output because it's everything from the cell color and the MPAS mesh generator. But anyway, it goes through all of this stuff. And by the way, if you're ever curious at what's ever happening or trying to debug or whatever, if you look at in any of these things, you can look at the run.py and it tells you what it's doing. And so here it's running the colmesh.py. So we always start out with run.py just so everybody knows that's always the reference point. But here there's a colmesh.py, and we go through and we explain exactly what we're doing here, which is what I summarized. And then, you know, if you have a question about this, you can always look down further and see what some of these individual steps are. And Xyler has gone through a great deal of work putting a lot of these executables inside the MPAS tools package, and then we also refer to the geometric features. These are two repositories, and so it's all quite convenient. We used to have to compile a lot of these tools externally on separate machines.
So Andrew has a question. He's asking, can the blockages and passages be made resolution dependent?
So that was what Xyler said. Right now, it's either you get them all or you get none of them. But we could potentially make them into categories or groups. That's not what we have right now.
Yeah, so what we'd found up till now is that if they're defined carefully, they're usually harmless at high resolution. But I think we also maybe choose not to use them at a strictly high resolution mesh. If you have, say, a variable resolution mesh and part of it is high resolution, it's usually harmless to have these blockages or passages in that high resolution mesh because they're already open or closed. That's right. What we found.
Right. So here I'm showing Japan, but another nice example was the English channel that I don't have in front of me. But basically, if you do a good job of centering these lines well within the water or well within the land, then when you're at high resolution, it doesn't matter because you're already inside of those regions. So then the culling also removes single cell wide river outlets, which can cause problem for sea ice because it can't advect. And then it does some special things for land ice cavities. Okay, and then so the final thing that you get here is coldmesh.nc. I tried to make that the same. I tried to make the naming uniform. Oops, there we go. And so here, if we look back here, if you guys are following along, then what you see on the output is coldmesh.nc, and there's also a VTK file that you can visualize in ParaView. And actually, I have this up so I can just show you. I took exactly the same thing, but for the cusp mesh. And so when you bring these things over, and this is what I got these images from, you know, you can go from the base mesh to the cold mesh to to the next step, which is the initial condition. So you can explore it visually in pair view as well, which is quite nice. Okay, and so then the final step is to go from just the horizontal mesh, the single layer, which has the MPAS standard for the mesh, and then everything that you need for, in this case, for an ocean. And so this is the initial state, and this is what you need the MPAS forward model for. And so if we go here into initial state, and then we can just run this one by itself if you want. It's already run, so then it's running MPAS in init mode. And so this is one, the reason we did this from the executable is that at high resolution, you can't do it on a single core. You really need the ability to do these things on many cores. And then also we have the full subroutines available from MPAS. So if you want to have a density or a pressure gradient or anything else, or any operators on the native mesh, you can do that in init mode, which is quite nice. And so then what you end up with is the initial state.nc, which has all of these extra variables, and then it makes a couple of PNG files. And we just added this last month because when you're making this, what we found is you really need to have plots that are convenient and I would say in your face to make sure that you don't have dumb errors, because it's easier as you're doing this stuff to not check things well enough. And so we made these two PNGs to just view the vertical distribution of the layers. It gives you here the min and max thickness of the layers, the bottom depth, and then this is just a partial image. We have a PDF of all of the variables with a min and max, and this is just a sanity check. But for example, if your links are off or if it did a partial download or something, it can sometimes end up with wrong data on these variables. So that's a way to check that. And so here in your directory, you can see the two PNG files are right there. Okay.
I have a question.
Mm-hmm.
Can I ask a question?
Go ahead.
So I assume this is the step where the bathymetry, right, is included in a sense, because it's.
So in fact, I have that here.
Oh, that's topography. That's the topography.nc.
I didn't keep the whole thing. Oops. Sorry, I'm gonna break this, bring it to the front range. I hit it. So here's the bottom depth, and then here's the layer thickness, and here's the max level cell, the number of vertical cells. So you can also take a look at your distribution of all these things. Is that the question, Elena?
This is also where you would put in a different bathymetry if you wanted a different data set. So you would edit the name list, or you would actually edit Compass to produce a different name list that has a different, so we have a bathymetry database and it points to one in this particular test case, but you could make it point to a different data set and make sure it's part of our bathymetry database, and then basically use that.
I see. So it's part of the name list option.
Yeah, and like I said, we try and put all of our links here. So if we do an ls-l on star NC here, and then I'm gonna make this bigger. And so what you see here, and you should see this in your directory as well, that all of these files, they point to a certain place. So we have a common directory where we have all of these. But if you are on a different machine, or if you put a different directory in your config file, it would auto download all of these files. So this is just gridded data for temperature, salinity, bathymetry, BGC, whatever.
Mm.
And so it is all set up, and I say that here. So if you click on this link, it shows the public HTML page where it's actually downloading all this stuff from. And so actually, if you look at the full link right here, there's all of the files. And so if that's not on disk in the place that you specified, it downloads it, but it only downloads it once, and then it's there.
What about, so we've been doing a lot of changes with the vertical grid, you know, where we put the levels. Is that also a name list option? Do you have to change an XCDF file for that?
Those are flags or they're options in a Python script instead, right?
So in the directory that we're running, the old way was that we got the hard-coded the numbers of the thickness that we used in POP for the 60 layer. And the new way is this Python script right here. And so right here, line 61 through 66, those are the defaults, but then we can call them with, so it just makes a functional distribution of based on the total depth, the min and the max layer thickness.
So Mark, I think the easiest might actually be to show define vertical grid.
Oh yeah, right, thanks.
Because that's the one specific to this test case.
Right, that's better. Yeah, so you call this vertical grid that I just showed, and then you feed in those arguments. And so you can literally just change it right there to alter the vertical grid. And then you can look at that PNG file to see what you get. And so for these simple little test cases, I just did 16 layer. Okay, so I'm going to run out of time pretty soon. So I'm going to keep going. Okay, and so I thought everybody, it takes about a half an hour to run the cusp test case, but we can set it up. And so if we go back to, if you go back to your compass directory in the repo, okay, and then sometimes I just use a grep. If I'm not sure what the name is, I'll often just grep on something. And I don't know why list test case has been getting stuck a little bit today. Come on. And then it'll show these two test cases. There's an init, and then there's also a spin up procedure that goes directly from init. There we go. Okay, and so then we can do exactly the same thing, but we're going to do it with number 65, which is the cusp, which is exactly the pictures that I've been showing. Okay, and then we can go to there, and then after you set it up, I don't know what it's thinking about. I wonder if that's an IO thing on disk. So it tells you exactly where the directories are here. So usually after I do this, I'll just grab this right from here. I can CD into there. Okay, and if we did run from here, like I said, it would take about a half an hour. So I don't want to do that. Let's just go into the base mesh. Okay, so beforehand, it's just the links and the run script. But if I run it in here, actually, we're going to do one thing first, which is on the next one. When you're just fiddling around with things, oh come on, my screen is having trouble. There we go. My screen's not updating for some reason. I'm going to turn off my. Can you guys still hear me?
Yes, we can.
Okay, my fan on my computer just started. Okay. So I'm going to run it here, but before I do that, for some reason my Google Slides aren't updating. So define base mesh is where we create this lat/lon mesh. Okay.
Mark.
Yeah.
Mark, your slides 13 and 14 are the same.
Yeah, I wonder.
So is everyone, or at least mine are as well. So I think that they are the same.
I must have done something funny
Copied.
there.
I assumed you were going to animate them or something, but yeah, no. They're just copies of the same.
That's what was confusing me, and my fan turned on at the same time. So if you change this to 1.0. So this is the resolution of the mesh. Okay, so this DLON. So I am right now in defined base mesh. That's what was on the slide that I must have erased over. If you go into defined base mesh, and the longitude is, this is just the resolution of the lat-long grid for the cell width. So a lot of times when I'm just doing the initial design or I'm just fiddling around with it, I'll make it low resolution. So here, look, I'll put this on here. This is what I meant to do. Okay, that's what you want to change. And then you can run it. And what it does is it goes through a number of steps. And it makes an image at the end as well. So here it's going through these steps. And so I'm going to describe what it is that it's doing. And then it goes into Jigsaw. And Jigsaw is going to take a while this time, but we can just let it run in the background. And so this is a little bit more of the detail that I wanted to describe, because for those of you who will be involved in making or altering these variable resolution meshes, I want to hopefully convince you that it's really easy. And so this PNG is something that's made at the end, and each row is made up of a mask. So this is the next slide here. A mask that's just a GeoJSON file, and then a distance to the transition and a transition width. And so for this cusp mesh, I just went around the coastal United States and Canada, and then I gave it 600 kilometers for both, and then a 600 kilometer transition. And this is the mask that it makes. And it goes from 0 to 1. So if you zoomed in here, you'd see regions that are in between 0 and 1. And then we used a signed distance function from here, and then we can overlay that high resolution region just based on that. And so for some things like distance from coast, it's better to have some distance, like 600 kilometers here, if you want the continental shelves. But then there's other things that you might want to do. So like there's a step here, and this is just rough. I was just getting something in there where you say, oh, I want this region to be high resolution. And then maybe you make the transition distance to the transition is 0. So it transitions right there where you're putting that region. And so in the end, you end up with this, you construct it. You make a sequence of GeoJSON files, and each GeoJSON file has a step inside of this define, oh, here's where I put it, the base mesh. And so here, if you do an ls in this directory, it shows all of these GeoJSON files. So then you can think of two different ways of defining high resolution regions. One is more intuitive. You can go to geojson.io and literally click around. And that's often useful for, if you know specifically that you want to have a certain sea or channel or whatever to be higher resolution, you can do that. Or you have all of the tools available to you in Python, and you can load in a data set if you want to have these regions be based on something that's from some model or observational data set. And I'm afraid I'm going to run out of time. Let me go through the rest of my slides, and then we can open it for questions in case people have to go. Okay, so I showed you all of the tools, but I also want to talk about the process. Okay, and we've kind of struggled with this the past few years because you always make a mesh and you see some changes, and then we alter it. And so we came up with, and this is with help from Zyler and Andrew. We came up with a process and a naming system. So the main thing was that we have a single PR for a certain revision of a mesh. We use the PR on GitHub to discuss it, to alter it, and then finally at the end, when people sign off on it, then we say, okay, this is a revision 2 or whatever, and then we continue running with it or whatever, and we see deficiencies, and we go to the next revision number. And I think that'll help us just keep things sorted on what's what. I also wanted to mention that compass, I went through the compass initialization, but there's also a really powerful tools in here for testing. And this is really partly what it was designed for in the first place. So there's a regression testing. So there's regression suites that you can put together from a bunch of these tests. And when you run them, they can give you pass-fail, pass-fail, bit-for-bit comparisons from one test to the other. So you can compare them across different executables or different points in the repo. And you can also do some performance testing. It'll compare times on the timers across different ones. And so if you want, you can copy this in, and here you can just, this is taking too long. So it'll set up the regression suite all together like this. So the init one is the one that we just did, but it'll do all of these things. So the stuff that I always comment about on the pull requests, this is exactly what I'm doing. And then there's another flag for bit testing. And so then to do all of these tests all at once, it's literally CD into the top level, and then you run the nightly regression suite, and it goes through all of these tests. So that's one thing. And then my last slide is that I took you through the first 4 steps. So at the end of these 4 steps, you have the mesh, but it's not spun up and it's not ready for E3SM. And so then I listed the additional steps here. There's spin up steps and compass. And the nice thing about that is you have to go through a sequence of steps where you slowly make the time step longer and reduce the Rayleigh damping so that you can finally get to a full time step. And so Compass gives us a way to record all of those steps and make them automated. There's a number of steps to get everything ready for E3SM. There's a detailed list there, and we have some of that in place in an E3SM coupling subdirectory. And then to finally run it in E3SM, the last step is to put that new mesh name or grid name in all of the scripts. And there's an example there with a pull request.
Mark, that part's not complete at all.
That's
a whole other topic that's going on in a different place.
Yeah. Well,
because you're glossing over it like it's done.
Well, the main purpose of the training today is steps 1 through 4. I just wanted to say that there's a lot more to do after that.
But it's not there. So you shouldn't bring it up that way.
So for the purposes of people in this training, I think one should treat the E3SM coupling step as very much a work in progress and something that requires quite a bit of expertise to make use of right now. And it's, something that is likely to change quite a bit as the group discusses it further.
Right. So I certainly didn't mean to say that it was less work than the other parts. There's a lot of steps involved and a lot of detailed knowledge required. I just wanted to say that at the end of step 4, it's not ready for E3SM.
And step 8 is really step 5, right, Mark? There's nothing there.
Yeah.
Yeah. Okay.
I was skipping ahead. Okay, and so then if we just go back to this automated testing step, it shows you, I mean, PAS is hiding a lot of details there, but it says that it was able to run through without any errors. And then in some cases, there's some checking going on under the hood, but typically it's better for a bit for bit test because PAS then means that all the output compares bit for bit between the two, the before and after case. Okay, well, it's 12:59. Why don't I'll just stay here for a while, and if people want to ask questions or if someone's having trouble, we can also go through some of this.